Okay, so let's start. Uh, I'll rush through some of the slides as this material we have already discussed to some extent in our earlier interactions. So these slides are from vintage when it used to be a common course for all first year students across the disciplines, and it was offered by electronics and computer science engineering department, and that's why the name is EC 101A. But the syllabus remains the same, only the uh, number has changed. So your code for architecture department, it is AR112. The contents are essentially same. And as I told you, I am Manish Rikhande, and I am from earthquake engineering department across the road. So computers, as we have seen, these are information processing machines, and they effect transformation of data from one form to another. And in order to transform data, in addition to the data itself, we need a set of instructions about how to transform, right? And these set of instructions are what are known as programs, right? And they instruct the computer, the hardware, basic logic unit, how to carry out the transformation. And obviously, both of these need to be stored. Data as well as instruction needs to be stored for a general purpose computer, right? For example, the computer that we have here, we can make it do anything that we want. So it's a general purpose. It is not designed for any particular use as such. There are special purpose computers which are designed to do only one sort of a thing, right? And those computers are typically are sometimes they work in analog form. So those are analog computers, and they are much more accurate than digital computers. But for general purpose computing, digital computers are uh, the industry standard, and they follow what we call as von Neumann architecture. Right? A common storage may be used to store data as well as the instructions, and this conceptualization of the machine was proposed by a mathematician named von Neumann, and that is the architecture that is used in all digital computers. I just mentioned that analog computers are more accurate than digital computers. Can anybody answer that? Why they should be more accurate, or what is wrong with digital computers? Yes, yes. See, digital computers, they are based on certain quantization. They work in some quantum. I mean, there is a quantum leap for every next whatever next increment you take. So numbers, as I mentioned, numbers are not continuously available. Those are discrete set numbers, and there are certain in between which are not available, and those are discrete set, and anything in between is just void. Nothing is known. So there is something called quantization error, and no matter how large word length I take, there will always be some quantization. Whereas for analog computers, it's a continuous flow, continuous waveform, and it is all in full precision, right? But it is very difficult to design a reliable analog computer which will be general purpose. Special purpose circuitry can be designed, which is designed to do only one thing and do it well. That is very much possible to do in analog, but for a general purpose computing, digital platform is the most robust one and most reliable one. So these are the basic ingredients of von Neumann arc computer. There is a processor. Uh, you don't bother about taking the pictures. I will upload the slides on the classroom, so you can just download this slide deck. So there is a processor here, and as you can see, processor consists of arithmetic logic unit, and then these are the registers, right? And this is program counter unit. So this is what increments the instructions, and then this processor is connected with memory through this communication bus. It's essentially a communication channel, a conductor, which allows current to flow through of certain capacity, so data transfer. So there is it is connected to memory. Memory is loosely, it is referring to all sorts of storage. I discussed about different types of memory. There are level 1 cache, level 2 cache, and then RAM, and then storage, large scale storage devices. And then there are peripheral devices like this is, I mean, stylus, and this is also a device, right? So this is all interconnected. So this is, all these need to be communicating with each other, and for that you need to have some communication mechanism. So that is called a bus, right? So memory and cache, information stored and fetched from memory subsystems, right? So from the, for computation, I mean, as I mentioned, memory or storage locations close to the processor, they are faster, they are they have shorter seek time and shorter write time, and but their capacity is very small in order to keep the costs under control, because fast memory is obviously is going to be uh, costlier. So typical design requires a massive storage which is slow, but depending on which data is currently being processed, chances are that in the next set of instruction, you will need to work on the data which is stored adjacent to those locations which is being currently processed. So what is done is that neighboring data is automatically moved from that slow speed storage to cache memory, faster memory. And when the need arises, the data is fetched from the cache location, high speed memory. So that's what the idea is. Storage, memory, I mean, data needs to be stored in memory and it needs to be fetched from memory. And random access memory maps addresses to memory locations. I mean, that's what we discussed in the morning. The difference between 32-bit and 64-bit, that is the address space, how much memory you can uniquely identify, and that defines what is the chunk of random access memory, how large random access memory can be utilized on your computer, right? So memories are made of addressable cells, and currently one cell refers to 8 bits or 1 byte. So that's the standard, I mean, that's the building block. So you can say that 1 byte represents one memory cell. So memory address is an unsigned binary number, n bit, and the address space is 2 raised to the power n. There are n number of bits, and each bit can take two possibilities, 0 or 1. So total number of configurations that you have is 2 raised to the power n, right? So that those many different memory addresses are possible. Cache memory, that's faster than random access memory, and that keeps memory currently in use in faster memory. That's cache, that is called cache memory, so that your program execution is faster. The data can be accessed uh, relatively in shorter time than from accessing it from RAM or the hard disk. Structure of RAM, it's essentially different bits. So one memory cell, and then they are stored contiguously. And each of these has one address, unique address, right? And this is what when you, that number that you, funny number that you saw next to return code, process returned 0, and that funny number is actually the address from where this result is coming from. So which memory address it is, starting address of that memory where that data is stored. So here these are the memory address registers, so n number of bits, and then these are memory data register. So memory address register contains the address of the memory location, and memory data register, they contain the they point to the location of memory where you have data that is to be used for the computing. And this is the basic building block or block diagram of von Neumann architecture. So CPU comprises of arithmetic logic unit, and then there are some very high speed, very fast memory, very small amount of memory that is integrated into the processor. Those are called registers, right? So there are very small number, but they are very high speed memory. Then there is a program counter which increments and keeps track of which instruction has been executed and when to move to the next instruction. And then there are instruction register which contains exactly what instruction is to be passed on to this arithmetic and logic unit, right? And all this CPU is connected with this communication bus, through this communication bus to these storage locations where the data resides as well as the instruction resides. So both data and the instruction is fetched from this storage, moved on to this uh, instruction register, the instruction, and the data is moved on to registers, or that is kept on L2, L1 cache memory, and then the program execution happens in ALU. So basic sequence is fetch instruction from the main memory, what needs to be done, what is the precise instruction for processing of data. So that instruction is fetched from the memory, and then it is decoded. Please note that when you write the code, that is in higher level programming language that is designed to be legible to humans and as close as natural language as possible, almost as close as natural language, right? To make it understandable by the machine, it needs to be translated into machine code, right? So that needs to, that higher level language needs to be decoded into instruction set. That is, every chip has its own instruction set. So the compiler would essentially do the job. It will translate the program into instruction level chipset instruction. I mean, chipset level instructions. How that particular uh, information processing step is to be achieved by, in terms of a set of instructions that are understood by the processor that you have in your computer. And then once the instruction is there, you need data. So the operands are fetched from the memory, carry out the operation accordingly, and then store the results in registers, and then move it out to slower storage or bulk storage later on, flush it out so that it becomes available for fresh computation. So this is essentially the way sequence of anything being done on a computer. What fetch the instruction, what needs to be done, decode it in terms of machine language, get the data on which this instruction needs to be applied, process the data, store the result, flush out. And that's one step of the program. Program counter increments by one, next set begins. And that's how you move step by step. You move ahead in time. Right? So binary coding instruction set is a set of basic operations that a computer is capable of performing. And different processors have their own instruction sets. Therefore, compilers would generally be aimed at, or they are compiled, they are designed to produce code for a particular class of processors which follow a certain instruction set. A program compiled for a particular class of processors will not run, will not execute correctly on other class of processors. Right? And a program is a set of instructions arranged in a certain sequence for some computational task or some information processing, some kind of processing sequence. Data is the numbers or the characters which are used as operands for performing these operations, instructions. Binary encoding, because everything is based on digital circuits and logic gates, so everything needs to be transferred into binary format, right? So both program and the data, they are encoded in binary form for digital computers to understand. And because binary is easy to design, it's much more robust circuit to design, just to discriminate between two levels of voltage in the circuit, right? So they are much more reliable and compact. They allow construction of very compact hardware using base 2 representation. And that, in a sense, is the reason why we have base 2 number system for all digital computers. All digital computers today, they follow base 2 number system without exception. So how are numbers represented on a computer? As we all know, numbers can be broadly of two types: integers and float, or real numbers, right? So let's look at integers. We can have non-negative integers encoded as binary numbers. As I saw, I mean, different n number of bits. There are 2 raised to the power n number of possibilities, zeros and ones, and each of them corresponds to certain position, right? And that means there is a finite set of numbers available. If you exceed that, 2 raised to the power n minus 1, that is the largest number you can have, unsigned integer. If you exceed that, then it is going to be rolled back. And that rollback would be, uh, for example, let us say we have 3 bits, right? So each of these bits contains 0, and we can have 0, 0, 1, that is the next number. Then we can have 0, 1, 0, that is the next number, and so on until you have 1, 1, 1. If you increment one more, what happens? 1 goes here, you have 0, 0, 0. This is called carry bit, and that is lost. There is no storage to hold that carry bit. So eventually this is interpreted as 0, 0, 0, and this is what happens. And if you continue adding 1 to this, there is no way to distinguish this 1001 from what you had here. So this configuration is mapped back to this configuration. This is what you experienced in the morning. A very large integer would be rolled back into this range, into the range of available numbers, right? And how that is interpreted, that depends on the encoding, right? So in this case, we are looking at uh, non-negative integers. So this is essentially by using positional notation. This refers to 2 raised to the power 2 plus 0 multiplied by 2 raised to the power 1 plus 0 multiplied by 2 raised to the power 0, and this is equal to 0. Similarly, this one is equal to 1 multiplied by 2 raised to the power 0, 0, 0, and this is equal to 1, and so on it goes. So essentially, positional notation, same thing as you uh, did it in primary school mathematics, albeit using decimal numbers, face value, place value. You are doing it in binary number. Instead of powers of 10, you write in terms of powers of 2. That's all. So this is what essential configuration is. Mapping, you can that bit pattern can be interpreted as unsigned integer by simple positional notation. So unsigned integer is not a problem. What happens? The only thing is there is a finite size. Anything beyond that is rolled back into the range. Any carryover is promptly ignored. How do we represent the negative numbers, negative integers? So, as we discussed in the morning, the way we understand negative integers, or the way we understand integers, is that there is a whole number which defines the magnitude of the number, and there is a sign associated with it. So you can have sign and magnitude form, right? So we can assume that the most significant bit, this is the most significant bit because this carries the maximum weight as far as the power of exponent power goes. So this is called the most significant bit, and the bit corresponding to carrying the lowest power of exponent is called least significant bit. So in sign and modulus form, the most significant bit is considered to be the sign bit, and the number is interpreted as -1 raised to the power whatever is the content of sign bit multiplied by whatever is integer representation, unsigned integer representation of remaining bit field. Right. So in case of this 3-bit system, we consider these 2 bits as the range of integers. We will convert these 2 bits in the range of integers, right? So that would be 0, 1, 2, 3, and 4. Right? Is that 0, 1, 2, 3? Just 3. Right? And then you go one more ahead, it becomes 1, 0, 0. Right? So let me complete this 0, 1, 1, and then you have 1, 0, 0, 1, 0, 1. Right? So these are the two. If you see these two numbers, they are repeating. So this represents 0, this represents 1, this represents 2, this represents 3. 2 plus 1, 3. And the sign bit is 0. So the magnitude of the number becomes this is equal to plus 0, this is equal to plus 1, this is equal to plus 2, and this is equal to plus 3. Whereas next number sign bit is equal to 1. So minus 1 raised to the power 1 is going to be minus 1 multiplied by the magnitude of the number, that is 0. So you have negative 0 and then negative 1, then negative 2 and negative 3. So these are the possibilities that you have with 3-bit system. The most significant bit is the sign bit, and you represent numbers using sign and magnitude form. Works very well, very close to our understanding of integer numbers, with only one irritant, that you have two representations for 0. You can have either plus 0 or minus 0. That's the only minor irritant, otherwise all is well. Then you have biased representation. Biased representation is you effect a shift. You effect a shift. For example, all these numbers, they start from 0. So instead of calling this as the origin, I put origin somewhere in between. And this is the shift or bias. Right? So whatever is unsigned representation, I subtract this bias from that unsigned representation. And obviously I will get the signed representation. If I subtract a constant number from every possible representation, then for 0 I will get the largest magnitude, negative range, negative number, and gradually I will move towards the positive range. Gradually I will move towards the 0, and when bias, whatever is the bias number, if it is subtracted from bias, that becomes no 0, new 0, and after that you will get the positive numbers. Right? So it's essentially shift of origin. Instead of calling 0 as the origin of number system, we shift it a little bit by a constant margin. So every unsigned representation is set off by certain margin, or certain constant number is subtracted from that, and that I consider as integer representation. Right? So that is what we call as the biased representation. Essentially shift of origin, interpret the number as unsigned integer, and then subtract a constant offset, and that constant offset is approximately one half of the total range. That's only when you will get approximately equal range of positive and negative integers. Right? And that one half is, if there are total number of possibilities is 2 raised to the power n, so one half of that is 2 raised to the power n minus 1. Right? And then one sub offset from that, because we count 0 with positive integers. right? So this is conceptually very nice, but it is inconvenient in implementing arithmetic. You need to keep track of this negative bias. If you add two integers, your bias will get added, isn't it? Your integer I1 is represented as I1 bar plus some bias, and another integer I2 is represented as I2 bar plus bias. If you add these two integers, bias gets added, right? That needs to be negated. I mean, integer scale is the same. Just by the addition of operation doesn't mean that you are introducing bias as many number of times. Bias has been introduced only once. So that needs to be compensated. And therefore, although the conceptual idea of representation of integer by shift of origin is very appealing, design of arithmetic circuit using this representation has its own issues, right? And confusing and error prone. So this is generally not used in practice unless working with very trivial kind of arithmetic calculation. We'll see where that happens, where the compensation can be managed very easily without any confusion. So finally we come to most widely used representation of negative integers, signed integers, so to say, that is called 2's complement. It's like complement. What do you mean by complement? Complementary angle. We extend the same concept. Two angles add together make up 180 degrees, right? So you have one angle, whatever is you subtract from 180, whatever is left is called the complementary angle to that. Yeah, जो भी है यार, ठीक है. So 2's complement of a binary number is the value obtained by subtracting the number from a large power of 2, next large power of 2. So for example, if you have, again we are, if you look at it, we are using the limitation of integer representation to our advantage. We are trying to use the phenomena of overflow, the rollback, right? We'll see how that happens. So specifically 2 raised to the power n, these are the integers, total number of integers that are available for n bit number system. We subtract whatever number we have, we subtract it from one bit higher. I mean, just we add one more number to that, and whatever number we get, that we subtract. We'll see the how it works in practice. So it is used to represent the signed integers on digital computers such that, let us say, I have certain bits, 3 bit plus, let's say if this is a positive integer and this is its negative counterpart, addition of the two should be equal to, it should be equal to 0, right? So if this is I and if this is minus I, this should be equal to 0. It really doesn't matter if the addition is this, carry bit is discarded anyway, right? That's the whole point. So if I have a number I subtract it from this number. Whatever is left is the negative integer. That's complementarity, right? So you try to convert what was supposedly a limitation of digital computer to your advantage. To satisfy the rules of arithmetic works perfectly fine. 2 minus 2 should add up to 0. That's what you get. So no amount of explanation in words can explain this as nicely as actual addition and happening when you see the numbers adding up to 0 actually. For all practical purposes, they do not add up to 0, but practically it is 0. So in an n bit binary number, the most significant bit is the 2 raised to the power n minus 1 place. In 2's complement, its place value is negated. So it is given the negative weight, right? So it becomes negative of 2 raised to the power n minus 1, and it is also called the sign bit because it defines the sign of the number. So how does it work out? A quick way to determine 2's complement of a number is flip all its bits. So if something is 0, make it 1. If it is 1, make it 0. And then add 1 to the least significant bit. The resulting number is what you have is the 2's complement representation. Right? So for example, we have this example worked out. 0, 1, 0, 1. Flip the bits. It becomes 1, 0, 1, 0. Add 1 in the least significant bit. The number is 1011, and actual number in decimal representation is this one carries negative weight. So this is equal to 1 multiplied by 2 raised to the power 3, right? This is 0, then this is 1 multiplied by 2 raised to the power 1, and this is 1 multiplied by 2 raised to the power 0, and that's minus 5 in decimal. And if you add this number with this number, what do you get? Let us do that. What do you have? 1011 and 0101. This is 0, 1 carry, 0, 1 carry, 0, 1 carry, 0, 1. And this is discarded. So you have plus 5 minus 5 adding up to yield 0 for all practical purposes. Right? No further complication, no further compensation required for taking care of the arithmetic, which would be there, which would be essential if you had used biased representation, that is constant offset. Right? So essentially the same operation, adding up positive integer with its negative counterpart in 2's complement, and you get one carry bit which is discarded, and rest of the bits are all zeros, and that is interpreted as 0 by the computer. So these are small is range 4-bit pattern, different integer representation. What do they mean? What do these 4 bits map to in case of different convention, different formats? So unsigned integer decimal equivalent is it starts from 0 and 4 digits all ones, 4 bits all ones, it goes up to 15. Total number of 16 possibilities. That's 2 raised to the power 4. There are 4 bits. Each bit can take two values, 0 or 1. So there are total of 2 raised to the power 4 possibilities, and that ranges from 0 to 15. In case of sign and modulus form, it goes from plus 0 to plus 7 and minus 0 to minus 7. The range is evenly divided, with one minor irritant being 0 can have sign. 0 can come with sign. It can be positive 0, it can be negative 0. Then, yes, 1011. Which one? Yeah. No. Why should it represent minus 3? 1 for the sign, it's not that. It is this. 1 and the weight is negative. For the most significant, the position value is negative. That is how it gets sign. So don't confuse it with sign and modulus form, right? Uh, you forgot. I mean, this is the in 2's complement. The MSB, the place value of the MSB is negated. So instead of 2 raised to the power n minus 1, it becomes negative of 2 raised to the power n minus 1. Right? So that's all. Once you do that, then you have this 1 is there, and then this is negative of 2 raised to the power 3. Right? So this becomes what? 8, minus 8. Minus 8 plus 3, so that's what you get, minus 5. So sign and magnitude, they are evenly distributed between positive and negative integers, with one caveat that you have two representations of zeros, plus 0 and minus 0. Biased representation, it ranges from minus 7 to plus 8. Right? One extra representation is taken as 0, so that is counted in the positive range. Right? So not equally balanced, negative range of numbers is 1 less than the positive range of numbers. So that's another minor detail that you may like to note. It is finite, number line is finite, that is 1, and it is not equal. Positive and negative, they are not equal. You have more on the positive side, less on the negative side, slightly, but that's a fact. So they are not equal. Then 2's complement, again you have uh, minus 8 to plus 7, right? And that's the complete range you have. So different bit patterns, they can mean different things depending on which encoding is in force, right? And therefore, I did not take call. I am not aware of what encoding is used for representing signed representation when it reports that number return 0. Not sure. Didn't bother to check. Maybe if I check out, I'll let you know. But most probably it is 2's complement. Multiplication of integers by Booth's algorithm. Let's not bother about it. It's a I don't want you, or when I teach this course, my idea is not to see whether you can punch numbers on your calculator. That is a given. The idea is to test whether you know what numbers to punch, when to punch, and how to punch, in what sequence to punch. Right? So this is Booth's algorithm is a sequential set of instructions what to do when, and I'm sure all of you can figure it out if you go through that algorithm. It's a sequence of logical step of operations. So nothing difficult to uh, worry about. So let's omit that part. What do we do? So we now come to the other number that is available on the computer. Floating points or real numbers. The floating point, because that separator, the point which separates the whole part of the mantissa from the fractional part, can be floated by suitable change in the exponent field, right? So that allows you to represent very large number from very as well as a very small number, and that is necessary for any scientific computation, for any computation for that matter, because computer by design is a finite machine. There is a limit to what I can store, what is the largest number that I can store, what is the smallest number I can store. If I go by the integers, I cannot represent anything smaller than 0, right? If I have to do a calculation of some atomic nuclear chain reaction, how do I do that? Fission, not possible to model if I cannot go beyond less than 0, right? So inherently incapable of the infinite numbers on the real number line, the computers, and therefore only a finite set of discrete numbers can be exactly represented. Scientific computations require very large as well as very small numbers. Integers do not serve the purpose, right? The smallest that can go is 0, nothing less than 0. A proper representation of fractions is needed. The floating point representation, the standard format, 2.35, just some random number, exponent plus 9. The same number, if I change the exponent to 8, that floating point can be shifted to right. Right? If I change the exponent to 10, the floating point can be shifted to left. The same number can be represented as 0.23533 multiplied by 10 raised to the power 10, decimal number system. Right? So the whole point is you can keep on changing, and therein comes the need for standardization. If there are so many different ways a floating point number can be represented, how do I decide which one is what? There are practically infinite ways in which I can represent a particular number. One number can have infinite manifestations, infinite representations. So which one should I consider as a standard representation? Right? But we'll come to that standard representation. But the fact of the matter remains that this floating point representation allows us to represent a very large number as well as very small number by suitable change of exponent field. All that we need to do is change the exponent field. So 10 raised to the power some large negative power would represent a very small number. 10 raised to the power some large positive power would represent a very large number, which would serve the purpose of scientific computation. So normalized floating point numbers, they are represented as plus or minus, can be sign m0 dot m1 m2 etc., multiplied by beta raised to the power e, that's the exponent. Beta is the base of the number system which is used for encoding, representing the number. The requirement for m0, the whole part of the mantissa, is it should be greater than 0 and it should be less than the base of the number system. So for decimal numbers, it has to be some number between 1 to 9, right? So whole part can be any number between 1 to 9, and for binary numbers, there is only one possibility, that is 1. The whole part has to be equal to 1. So binary system, the normalization condition implies that the whole part of the significand, the number, will always be equal to 1. And that leads to the concept of hidden bit. Since it is by definition is going to be 1, why bother wasting some storage, 1 bit, on storing that 1 which always has to be 1? We can just assume that it is 1 always and don't bother storing it at all. And that leads to the concept of hidden bit representation. Floating point whole part is always considered to be equal to 1, and it is not stored at all. It is interpreted as 1 point fractional part, and it is only the fractional part which is stored. So single precision floating point numbers, they are represented by using 32 bits, that is 4 bytes, and out of those 32 bits, first, the most significant bit is the sign bit, that is reserved for sign, again in the same, using the same notation of sign and modulus form. Remaining 31 bits, the next 8 bit next to the sign bit, they represent the exponent field. What is the power of 2 that this number should represents, the scale, right? So the exponent field 2 raised to the power something. So what is that something? So those 8 bits represent that, contain that number, and obviously this has to be a signed number, signed integer. Exponent is always integer, but it is a signed integer. So 8 bits signed integer represents the exponent field. Remaining 23 bits represent the fractional part of the significant number. Please keep in mind, one whole part is always there. It is assumed to be there always. So the number is essentially 1 point, whatever is the fractional part stored in 23 bits, plus or minus depending on whatever is the sign, multiplied by 2 raised to the power exponent field, whatever is the exponent. Double precision, just the double capacity. Instead of 32 bits, you have 64 bits. Out of 64 bits, one is the most significant bit, is again sign bit. The exponent field is now 11 bits, right? And next 52 bits, they are the fractional part. They store the fractional part of the mantissa, right? And because of one hidden bit, you get one extra bit of precision without actually using that bit. So using 23 bits, you can get precision of 24 bits for single precision. Using 52 bits for representing the fractional part, you can get a precision of 53 bits for double precision numbers. So normalized floating point numbers, they are represented as minus 1 raised to the power s, whatever is the content of the sign bit, so plus or minus, multiplied by 1 point, that 1 is always there, hidden bit, 1 point, whatever is the fractional part, multiplied by 2 raised to the power exponent field, whatever is the integer that is encoded in the exponent field. That's how the numbers are represented. And because this number is in exponential format, 2 raised to the power something, the number changes exponentially. Magnitude is changing exponentially. That has certain implications. Please keep this in mind. I'll come back to this. Exponent e is a signed integer, and in this case it is used as a biased exponent representation, because when you operate, it's only two operands and it is very easy to compensate for adding up of the bias. You are only operating on two numbers and you know that bias is also getting added up, and you need to subtract one bias component. Not very difficult thing to do, right? So for this floating point operation, exponents will either be added, they will or be subtracted. So if they are subtracted, bias needs to be added, and if the numbers are added, then bias needs to be subtracted. That's all. So that's a very small compensation that needs to be done, and all is taken care of. Now, trying to be too clever doesn't always pay, right? While trying to save and trying to get extract more precision by using less resources, we end up into a very peculiar situation that the number system does not is incapable of representing 0, because 1 is always there. Whole part of 1 is always there. So no matter what negative exponent you put, you multiply it, 1 multiplied by 2 raised to the power some negative power, it is still not 0, right? So this is a direct fallout of standard representation. We tried to get too clever, extract more precision, and we land up into this very weird situation that no matter how powerful your computer is or how expensive your computer is, it cannot compute 0. You cannot arrive at a numerical result of 0 as a result of numerical computation using floating arithmetic. Integer arithmetic, 0 is a valid result. But using float or double, absolute 0, you cannot compute. And therefore, whenever you are in a need to compare the results which should be 0, please never compare with 0, because 0 can never be computed. It may be very close to 0, but it will never be equal to 0, and that decision will always fail. That decision check will always fail, because 0 cannot be computed. No computed number will be equal to 0, right? So how do we represent 0? It's just an assignment. When we start programming, it is always a good habit. Whenever I write a code, I always initialize all variables to some sane configuration. And 0 is an assigned pattern of bits. That is what we call as 0. So if I assign 0 value to some variable, bit pattern is set to a certain configuration, and that is considered to be 0, but that pattern cannot be arrived at through computation. It can only be assigned. So this is the IEEE 754 standard for binary representation, floating point arithmetic, binary coded decimal, binary format. So precision, single precision number, float, you have 24-bit precision. Although you assign only 23-bit, 1 bit is hidden, but still it is 24-bit precision. In double precision, you have 53 bits. Exponent maximum, you can get plus 127 in case of single precision and plus 1023 in case of double precision, minus 126 in case of single precision minimum, and minus 1022 in case of double precision. Exponent field width is 8 bits for single precision and 11 bits for double precision. Word length is 32 bits for single precision and 64-bit for double precision. Sorry, you should have indicated. Thank you. I kind of got carried away and